over a century, Eastman Kodak has been the world leader in imaging systems. From the days of wet plate photography to dry plates, roll film, color film, motion pictures, and fantastic images from space, Kodak has led the way. The past 100 years has been the era of silver halide images. Today, we're seeing the emergence of electronic imaging as an alternative to silver halide. Tomorrow, we will see these technologies coexisting to best serve customer imaging needs. This is why Kodak has established a world-class microelectronics facility in Rochester, New York, Kodak's world headquarters. Let's take a closer look. The process usually starts like this, with a concept review. A customer needs a special type of imaging device or integrated circuit to solve his problem. So, it starts in the minds of people skilled in this process. It might be the need for a new, better imager that has never been made before. But if the concept is sound, it will advance to design. With the help of CAD, or computer-aided design, and other design tools, the device will begin to take form in the mind of the computer, and in the minds of the design team. The first function of the design team is to find out what the customer really needs, then craft a silicon device that will meet that need. In our fast-paced, high-tech world, they must also be alert to new devices that may serve the customer better than existing ones. And finally, they must create new ways to generate devices. All of this to be sure that the customer's needs are met in the best possible way, in terms of performance, cost, and delivery. When a device has been fabricated, samples are evaluated in a device characterization area. This is part of an exhaustive series of testing procedures that are part of every step, from design through prototype fabrication and actual system performance. Here are some of the ways that image testing continues. After a device has been designed, tested, refined, and tested again until the design team is sure it is right, it is ready for manufacture. To fabricate integrated circuits in general, and imaging devices in particular, requires a remarkable building. This is because the fabrication must take place in a clean room. Kodak actually has 2 of these rooms at this location. This one is for the fabrication of custom devices in production quantities. It is a Class 10 clean area. This clean room specializes in low-volume custom devices and research and development. The high-efficiency HEPA filters and the laminar, or non-turbulent airflow, are 99.99% efficient in removing particles 0.3 of a micron in size or larger. The yellow lights are required because these are really photolithography darkrooms, but more of this later. The fabrication process actually begins in white light. The quality of incoming single crystal silicon wafers is measured in this process test area. The process control computer schedules and monitors the processes in all the clean areas. It is the CAM half of CAD-CAM because it helps guide the scientists and technicians through each step of the very complicated fabrication process. The basic fabrication cycle consists of 5 major parts: clean, deposition, patterning, etching, and doping. First, each wafer is put through a mechanical scrubber. It will remove foreign particles down to the size of 1/10 of a micron. Then the wafers are cleaned chemically. Besides the ultra-clean air, the water used in all these processes is purified and deionized, and all other liquids and gases are purified before being piped into a clean area. Next, various materials will be deposited on the wafers in special furnaces. Of course, these tubes use the latest in robotic loading and cantilever arms to reduce particle generation and hence improve the quality of Kodak's solid-state devices. Here we grow oxides, deposit polysilicon, silicon nitride, low-temperature oxides, and plasma-assisted silicon nitride. There are many special processes depending upon the type of device being fabricated. In here, the fabrication steps take place in an area similar to a photographic darkroom, called a photolith room. This is because, first, the wafers are coated with a layer of photoresist. This is similar to a photographic emulsion. It is sensitive to light. The layer of photoresist is developed away chemically, leaving the photomask pattern on the wafer. Next, the photoresist is exposed to ultraviolet light in a mask aligner. Exposure tools include both one-to-one projection aligners and reduction wafer steppers. The remaining photoresist protects the underlying material during an etching sequence. Most of our etches are done using plasma or reactive ion etches due to the fine geometries used in Kodak imagers and integrated circuits. The final major process is doping, or ion implantation. This adds impurity ions to selected areas of the device to create some of the special characteristics required by the device design. This whole 5-step process is repeated over and over again until the number of layers wanted for a particular device have been built up. This may be as many as 12 or 15 layers. A layer of aluminum is deposited over the entire wafer. This will provide electrical connections throughout the imager or integrated circuit. And here's a wafer containing a great many individual devices, ready to be cut apart, tested, and packaged. A unique Kodak advantage is our ability to fabricate imagers with integral color filter arrays, so that a single imager can reproduce full color. The equipment used is similar to that used for standard devices, but the process uses non-standard photoresists and other special materials for the arrays. This is a proprietary Kodak process. The device engineering area receives the finished wafers after fabrication. The wafers are tested for correct process parameters, such as voltage breakdown, leakages, and functionality. Here, a wafer is passed if it has all the correct process parameters. Each individual device, or die, is checked for functionality and good die art, and then identified for packaging. The individual imagers or integrated circuits are cut from the wafer with a micro-diamond saw. Those that meet Kodak's high standards are ready for packaging. Each individual imager or die is bonded or die attached to a package which is often ceramic material. Electrical connections from the package leads to the die are accomplished by state-of-the-art ultrasonic wire bonding. The package provides a protective environment for the die, and it also permits easy electrical connection to the outside world. This is provided with 1 mil aluminum wire. Testing never stops. At many points there is inspection for such things as correctly cut dice, quality bonding, and clean devices. After packaging is completed, there is more testing using high-speed automatic testing instruments with state-of-the-art image processing equipment. This is done at normal system operating conditions. Many special packages have to be designed and made for special die, like this 3.5-inch linear sensor, a unique Kodak product. Once the imager, or any integrated circuit, has been fabricated, it must fit into a carefully designed and manufactured electronic subsystem. The imaging electronics team starts with a versatile breadboard so they can refine every parameter of the process before going to a compact, low-cost implementation. It takes many skilled people to hone and fine-tune an imaging breadboard system to make sure that everything is right, and to assure the manufacturability of the eventual system. So, once again, CAD/CAM is used, and once again, it is the skill, experience, and dedication of the Kodak people who make it work. Here's another example of what we mean by manufacturability. This is a robotic pick-and-place machine that places die parts on a substrate with superhuman precision. We're using more and more computer-operated automated machines. This is commonly referred to as computer integrated manufacturing. This pick-and-place machine in our prototype facility is an exact duplicate of one used by manufacturing facilities, so we know that they will be able to duplicate what we are fabricating here. As we move into the era of electronic imaging, there are many different problems to be solved, different from silver halide imaging. For example, noise is an inherent problem in electronic imaging and electronics in general. It simply means any unwanted signal. As an analogy with a high-performance audio system, we strive for a high signal-to-noise ratio. This world-class low-noise breadboard is an example of the custom-designed and custom-built support equipment we use to test our own devices. The ultimate test of an imager is, of course, how well it images. This system is capable of producing images that exceed the resolution of your home TV set. For instance, the Kodak megapixel imager should be compared to 1,000-line HD TV systems rather than 300-line home receivers. This is an emulation of the Kodak Mega Plus camera, the heart of which is the Kodak 1.4 million pixel imager. The NTSC television system you are watching can only hint at the remarkable high resolution. The world's highest density sensor. It is in use now, serving any industrial purpose that requires high-definition inspection. What does all this add up to? It shows that Kodak has indeed established a world-class microelectronics facility that is at the leading edge of this science, ready to serve you in any way. The Microelectronics Technology Division has already created many firsts in electronic imaging. This is the Kodak EctaPro 1000 motion analyzer, based on the world's fastest image sensor. The world's highest density sensor, packing 1.4 million pixels onto a 7 by 9 millimeter chip, is the imager in the Kodak Mega Plus camera. It is the highest resolution electronic camera available. At Kodak, tomorrow's microelectronic technology is here today. The facility is here. The technology is here. And the dedication to advancing the leading edge of technology and solving the needs of our customers. In today's world of electronic images, an audience can be dazzled with zooms and flips and split screens and comet's tails, with posterization and polarization and special visual effects of every kind. Images are manipulated in 1,000 different ways, but first, that electronic image must be captured on an image sensor. At the Microelectronics Technology Division of Kodak, we're making these imagers better than any place else in the world.